Okay, let's get started, everyone. So first of all, and that's very in due time, happy Leap Day, everyone. So, and it happens to be on a Thursday, which is also our Leap Day. So that's really great. So today it's a great pleasure to have our very own Ryan Abernathey. He was one of the primary PIs actually involved in the early write-up of the Leap proposal. So it's a great pleasure to have him here today. Ryan is a physical oceanographer by training, kind of drifted, and that's, I think, the term, to become more of a data scientist, over the years and getting more and more interested in data and data structure. And he's been doing a lot for the community in terms of providing really modernized data infrastructure that we can use. And we're actually using a lot of that as part of Leap as well. He got his PhD back from MIT, got a Sloan proposal of foundation funding back then when he was a professor here. He was a professor at Columbia in physical oceanography and at Lamont and the Department of Earth and Environmental Sciences for a few years. And he decided a few years ago to actually start his own company. So he's been starting his startup. He's been a co-founder, a CEO for a company called Earth Mover. And really what he's been trying to do is trying to address kind of the bottleneck that he's found over the years, which is in terms of data infrastructure, especially when we think about climate data and spatial and temporal data at scale, right? So, and we'll hear more about that. So very happy to have you here today.
Thanks, Pierre. Appreciate that. It's great to be here. Great to be here on Leap Day. And fun to think back about how far this project has come since we first started working on it. What I want to do today is really give an update to all of you, the Leap community, about what the heck I've been doing for the past year. Maybe you're curious. I'm going to do this by telling sort of my personal story about my journey through data infrastructure. Pierre mentioned, a couple different roles. So I'd like to be very clear about this at the beginning of the talk, right? So I can wear a couple different hats, and I will wear a couple different hats at this talk. Pierre used the past tense. I am still a faculty member at Columbia, so as far as I know, maybe there's an email waiting in my inbox changing that. But I've been here for 10 years, working, leading a research group working on ocean circulation and climate. I've also been very involved in the open source community, mostly through the Pangeo project. And I'll talk about Pangeo and what that is, but that's really me wearing the hat as like a coder, software developer, working on tools, hands-on. And then more recently, this hat as a sort of startup founder and CEO, which is a very new and sometimes very uncomfortable and strange hat for a scientist like me to be wearing. And I'll wear these different hats at different times in the talk. And in particular, at the end of the talk, I'm just going to put on my hat as a startup founder and just give you our pitch about what our company is and what it's doing. And I'll try to be very clear about when I'm doing that and sort of, box that from the bigger picture perspective, the talk that I'm giving. So that's the plan. Why should you guys care about data infrastructure, right? Why is this an interesting or important topic? Isn't this just a IT issue? I think many of us here are motivated by the desire to take climate action, not just do research, but really operationalize what we know about the climate, what we're learning about climate change to really address adaptation and mitigation. And that operationalization requires us to rethink how we work with data and upgrade how we work with data. Another big angle, what's going on with my slides here, is open science, right? So I think a lot of us are also excited about the vision for open science, making science more transparent, more reproducible, more accessible to more people. And that also requires us to upgrade our data infrastructure, because the way we do things, the status quo, actually can really hinder that open science goal. So those are sort of the two high-level motivations why I think everyone here should actually be interested in this topic. I've become obsessed with this topic so much that it took over my career. You don't have to go that far, but 45 minutes of attention, hopefully you can muster, right? So this is kind of the outline for the talk. It's a personal history of, my experience with data and data infrastructure, kind of moving through my journey from a PhD student to a professor, and then, you know, to the present day. And so I'll start by talking about, I'll give a sort of, you know, indictment of what I see as the status quo, the previous way of doing things. And in many cases, I call this the past, but in many cases, we are here, you know, in Leap kind of already in the future, but many people, I would say most people are still not, and are still using the approach to data infrastructure that I'll describe as the past. And then finally, you know, I'll talk about where I think things are headed and what we need to be doing. And that's, of course, where I'll be talking about our company, which is, you know, conceived of to address those challenges. Okay, so I call the past like files and servers, right? And I'll explain what I mean by that. But basically, the standard sort of status quo way we work with data in our field is that we've got servers and then we download files, and like that's it. That's our infrastructure, right? And everyone laughs because I guess you're all familiar with this. So here's a couple different types of computers. I can see everyone's got some laptops, so that's part of your data infrastructure. That's what you might use, and maybe that works fine. You know, in our group for a long time, we had like this big server. We had like big server, a bunch of RAM and CPUs in the closet. People get together, they buy a cluster for their, you know, department, and then finally, you know, once you get some funding, you can get on one of these big fancy HPC systems like, you know, NCAR computer or NASA or DOE computer, something like that, right? And so what do these all really have in common? Like, what is the baseline that we can sort of count on, that we can use on all of the systems? Well, basically they're all running some kind of Unix, Linux type file system, operating system. They have the ability to download files and the ability to run some programming languages. And that's kind of like how we do science, and you're expected to do this through the terminal. Like that's basically like the baseline, what we can count on any system we use. What they don't even necessarily guarantee is access to the internet. So if you're on one of those fancy agency computers, it's walled off from the internet. We don't use databases for the most part, and I'm going to come back to this. I think we need to start thinking about our data in terms of databases rather than just a bunch of files. We don't really use services, APIs, any fancy IT stuff here. It's just a bunch of files and scripts, right? And in general, the user interface or the user experience for the scientists is pretty lousy. It's just that terminal type thing, run your code. Now, of course, there's exceptions, but this is the baseline. And this is what I was trained on. So I have a picture of myself as a grad student. This was what I was taught. This is how we do it. You get the files, you run the scripts, you get the figures. That's what infrastructure is. A lot of this infrastructure was really, particularly as you move to the clusters, the servers, was designed for simulation. We're all familiar with simulation in Leap, you know, running climate models, and it's pretty good for simulation. It works at what it's designed for. So what is simulation? You know, we're basically going from some equations, Navier-Stokes equations, throw them into a big supercomputer, and out comes a bunch of data, some predictions, some forecasts, model runs. And so that process does, it takes a very tiny amount of data, which is basically just our code, and it explodes it out into this huge amount of data, right? But then that's really only the beginning of the scientific process there. In order to actually learn something, we need to then do something with that data and reduce it back down into something, some insights, some understanding, some predictions. So this process of reducing a big blob of data down into insights, understanding, predictions, call that data intensive science. A lot of AI and ML would fall in that category, but so does just basic statistical analysis, visualization of weather, climate, and geospatial data. Right? And so, and the process by which we do that is very varied. Like there's no standard template of like what that looks like. Everyone kind of does it a little bit differently, but at the end of the day, that's what we're doing with this data, right? And in particular, I find that this data intensive science is really hard to make it reproducible, right? So here I'll sort of digress a little bit into what I think, like, this is sort of some metaphysics of how I've come to think of like, what is an actual science project? Like, what are we doing? Like, this is particularly relevant in the context of reproducibility. What is the thing we're trying to reproduce, right? I would say most projects out there, like individual units of science projects, are basically taking some existing data and perhaps also bringing in some new data. If you're an observationalist, you've actually gone out in the field, collected some new data. A lot of what we're doing is taking data that already exists, ERA 5, existing model runs, existing satellite data, and basically running it through some sort of code and producing some sort of outputs. And those outputs are either figures that we're going to like put into our paper, or maybe they're new data, a new data set that then we're going to use and feed downstream to the next science project. So I started to think of all of science as basically like a chain, a graph of these projects that are consuming data and producing new outputs, and then consuming data and producing new outputs. And it's a very large, complex graph, and it's amazing. It's very hard to reproduce this type of project. What do you need to reproduce this type of project, right? Here are some of the sort of checklist of what it takes to truly reproduce one of these projects. First of all, you need the source code of like what was run. And that's when a lot of us think about reproducibility. That's kind of where we start and stop. It's like, well, I shared my code, like my project's reproducible. And if you're doing that, that's already great. That's a big step forward for reproducibility. But there's a lot more, right? Maybe does that code actually run? Can we install the software? Can we recreate the environment, all the dependencies where it ran? Can we get the input data? We need these inputs. Are they going to be accessible? Are those hard to get? Are they private? Are they secret? Are they not shared? Can I actually run the code? In the case of big data, maybe you can get the code, maybe you can even get the data, but if it's a very expensive computation, you're still not going to be able to reproduce that. And then only once you've checked all 4 of those boxes can you address what I think is usually the most serious barrier. Does the code actually work, right? Like, and if you've ever tried to reproduce someone else's science, you know that this can fail at any one of these points, and often usually does, right? The thing I really want to focus on that I see as one of the most challenging barriers for the type of thing we do is this data question. Because all of this stuff can work, but because of the way we do data infrastructure, it's actually very hard to just access the data someone else used for their science project and get the same result. I'll say we're doing a great job of that within Leap. I think the use of our hub, this collaborative environment in the cloud, we're already quite a few strides beyond this. The general pattern that we've taken in the past is to create what I like to call data fortresses, right? And maybe we are creating one a little bit in Leap as well. So what is a data fortress? So like this is us, this is Columbia, and we've decided we have a bunch of data intensive science that we have to do. And so we want to support our researchers to do it. So what we're going to do is get all this data from all these different providers that we know about, and NASA and all, et cetera, all the user such, and we're going to put it on a supercomputer in our basement. And now we've got this amazing data fortress. And we're going to do all this science with it, and then we're going to share our code with our colleagues at another institution. And the first line of everyone's script is something like this, right? Open some files that exist only in this data fortress, terabytes and petabytes of data. And so that's what I mean by this is where reproducibility very often breaks down, right? We also have this wonderful policy where the minute you leave our institution, we immediately discontinue your access to that system. So if you've ever been a postdoc, supervised a postdoc, you'll know that the research does not end the day the postdoc leaves one institution and goes to another. Yet for some reason, we think that their access to the infrastructure should, right? So to summarize, here are some of the problems that I see with this traditional way of doing business and working with data. First of all, just this emphasis on files as a medium of data exchange creates a lot of work. So how many of you have just spent hours upon hours of just downloading and organizing files just so you are ready to actually process them, right? Furthermore, that's not really collaborative, right? Like even if you put a lot of work into doing that, you can't really like get credit for that as a scientist. You can't share it with someone else. There's no way to like encapsulate that effort and share it and recognize it. It's really expensive to do this type of science, right? So typically we're working with terabytes or more of data. And so you need these big computers to do this sort of work. And this, limits who can do this type of science. So we are very well resourced here at Columbia. There are partners that we have within the US and internationally who really they don't have that cluster in the basement, and they're not going to. And so they're just left out. These sort of security approach we take to our servers and clusters is designed to limit access to outsiders. But when we talk about collaboration and reproducibility, what we're talking about is giving other people the opportunity to use our data, use our code. And so those two things are really opposed to each other, and that is limiting collaboration and reproducibility. And finally, I find that all of these servers, all these clusters, they're kind of a special snowflake. You have to kind of tune things to work in one, and then it doesn't work in another. You can't easily move your project from one system to another. And so these are some of the problems. So the present era, for me, starts around 10 years ago, when I started to observe really an explosion of big data, new, much larger data sets coming online, and a lot of exploration of new technologies that could help change the way we interact with data. And a lot of that involves the cloud. And so I'm going to talk about big data, and I'm going to talk about the cloud. For me, here was personally the trigger for me that set me down this road away from being like a normal, physical oceanography and being this sort of data obsessed person. So this is a gorgeous ocean simulation. Many of you in the room may know it and have worked with it. It was run, at this point, it was run almost 10 years ago. And it highlights why we have such big data in Earth system science. So I'm a physical oceanographer. I'm interested in ocean mesoscale turbulence and how that influences global scale circulation. So fundamentally, to model that problem, we need to resolve the mesoscale, which means having model resolution of around one kilometer. And then we need to also resolve the basin scale, the global scale. And so those scales are constrained by the problem we're studying, the deformation radius, the size of the planet. There's not a lot we can do really to get around it. And fortunately, we have supercomputers that can model the ocean that way. But the problem is, and we can run that model, and it's great, and it's beautiful, and it's amazing, and it spits out many petabytes of data. So petabytes is 1 million gigabytes, right? It's like what's after terabytes. It's really vast. And so when I first encountered this simulation, I sort of realized how screwed we were. Right? Because there was such enormous potential to do amazing science with this data set, but the tools, the systems that we had were just totally not up to the task. And so that set me personally on this journey to try and do something about that, which now I'm still on. And 10 years later, we're starting to get some papers out about this simulation, finally. So this is obviously not just one rare example. Any data archive you look at, you can see this trend, whether you're looking at NOAA's data, NASA's data, CMIP data. This is driven by just technology. Sensors are becoming higher resolution. We can observe data more. We can gather more data more quickly. Computers becoming faster. They can simulate data more quickly. And so this is a really kind of existential problem for our field. Now, I think a really influential milestone in the way our community thought about data infrastructure was when Google launched Google Earth Engine. So show of hands if you've ever actually used Google Earth Engine. Just one person here. That's maybe two. That's really interesting to me. So Google Earth Engine, it's not really aimed directly at us. It's aimed at the remote sensing community as a way to work with planetary scale imaging, like think Landsat and Sentinel, that type of data, right? And rather than having to download all those files, which is what everyone used to have to do, just log into Earth Engine, see all the data there. It's out there in the cloud somewhere. Write some little script in a window, and it would just go process petabytes of data and just give you back a figure. And it felt like magic to people. The user experience was so much better than trying to do that type of processing on a supercomputer or download all those files to your laptop. So it really opened people's eyes to what was possible with cloud computing technology. Of course, Earth Engine isn't for every application and isn't for everybody. And just from a sort of practical point of view, it's something that was created by Google, run by Google, and so it's not necessarily inclusive of every use case and scenario. So it itself doesn't necessarily solve all our problems, but it created a template for what a solution could look like. And out of that, eye-opening was born this community we call Pangeo. Sort of looking at asking how could things be better? And furthermore, how could we build systems like Google Earth Engine in a more sort of modular and open source way to have that same sort of capability to work with data, really fluidly. So Pangeo is a project that I helped get started back in 2016, 2017. And it's a community of folks who I characterize as obsessed with efficient data processing, who just really want to nerd out on this problem. How do we actually do this right? And that community is, I think, the strongest part of Pangeo, carries on today. There's a forum, there's meetups happening at conferences. And I think folks here may know a lot about this. It's a big part of LEAP as well. What this community does is work on software, open source software, scientific Python tools that work together to provide a really enhanced data analysis experience and that allow us to scale out our computing to work efficiently with big data without having to manage a lot of the details of how that works. And then there's an infrastructure and data and computing infrastructure component to Pangeo. So early on in the Pangeo project, we got access to some credits in Google Cloud way back in 2017, and we just started playing around and sort of started to figure out, how does the cloud work? What can we do? What's possible? It was incredibly freeing, and we developed a lot of really exciting prototypes for how to store data, how to provide computing access. Pangeo has followed this process that I think has been very effective, and I think is a good template for how we should be developing data and software systems going forward. It is very interactive between the users and the folks who are developing the tools and software. And that's not something that you can really say for the traditional way of doing data infrastructure. In general, the end users, who are basically grad students and postdocs, right? That's who we're talking about. And the people who actually have to do the work. They're not generally consulted in the design of like a new cluster, there isn't really a feedback loop there. In Pangeo, we managed to create this feedback loop between folks who are working on building software, folks who are working on deploying and maintaining these data systems, and the end users. And a lot of times, all three roles were in one person, sort of building things for themselves, solve their own problems. So I think this has been a successful pattern. Pangeo has grown to involve a collaboration, really international collaboration, participants from, across the world, academia, public sector, and a growing number of private sector participants who are using these tools and technologies to, accomplish all kinds of things. And so we're certainly on there. I put Earth Mover logo on there. I'm really proud of like this growth of this community. How does it work? What is Pangeo in a very basic way? What's the pattern we came up with? Well, first of all, who here has used the Leap Hub? About half of people here. So this is how our Leap Hub works. This is the basic data infrastructure. What we've got is a system that you connect to over the web, and we use Jupyter notebooks as that user interface. Just log in to your laptop, write code in your browser. Out there in the cloud, there's a virtual machine. Can have a bunch of resources, a bunch of CPUs, a bunch of RAM, running this open source software, tools like Xarray that help us easily query and work with data. And then that's connected to a big library of data, also up there in the cloud, that it can access very quickly, very efficiently. If we need to scale out to use big data, this type of system has the ability to just launch more and more sort of virtual machines out there in the cloud to process more and more data in a way that's fairly transparent to the user. And so it provides that kind of Google Earth Engine-like experience of, okay, I just want to process all these terabytes of data, just go and, see a little progress bar, and then you get your result back, right? And so this is the basic, our infrastructure that we came up with. And a big part of this is the use of these cloud-optimized file formats, right? And so I've been very critical of files. I've been saying, well, files, it's a pain working with files. What else is there really? And so that's what I'm going to discuss a little bit, and how we can store data in a way that gets us out of this sort of file mindset. And so Zarr is, there's a lot of buzzwords on this slide, but Zarr is basically a way of storing really large weather, climate, and environmental data sets in one object that is spread over many files. Right? So Zarr is not a file format like netcdf or grib or something like that. It's a little bit more like a database, right? And so it's a way we can take those big data sets, split them up into many objects, and then query that thing as one sort of virtual file or object. There's been a lot of work on this over the past years. It's come a long way. We had a hackathon for Zarr here in the Leap Center just 2 weeks ago, and Leap helped sponsor that. So this is a really important piece of technology for this vision, this ability to sort of break away from thinking about individual files and look at these big objects that represent data sets. So I'm very proud of the impact that Pangeo has had. It's really been adopted. People are using these tools on a daily basis at all kinds of different organizations, whether that's individual grad students or whether those are big companies and organizations like Microsoft or the European Space Agency. They have taken these building blocks and they have built systems, data infrastructure using these concepts that's really moved forward the state of the art. Pangeo has also been really, I think, impactful around open science. This idea of providing data and computing environments in the cloud sort of breaks us out of this trap where science is constrained by what compute infrastructure an institution can buy locally, right? And the servers they're able to put in the basement. So here's an example. We worked with the Coastal Ocean Environment Summer School in Nigeria and Ghana to provide a cloud-based environment for ocean and climate data to support the summer school. The scientists there, they had access to the internet, so they were able to connect to the system, access a bunch of computing resources, access a bunch of data, and do things that would never have been possible using the local infrastructure. And I should credit Paige Martin, a former postdoc who did a lot of the work to make this happen. I'm not saying we solved open science with Pangeo, but we found some patterns that I think can be used. And there's a lot more work to do here. So, coming to the end of this part of the talk, I'll offer some sort of reflections on what has worked well and what are some of the limitations of what we've done in the Pangeo project. Is it just me or is it really hot in here? I'm trying to figure out. Okay. So as I mentioned, I think it's been really successful in terms of adoption. People are using this stuff. It's not just a project for show, writing annual reports for some program manager. Like people use these tools, and that has empowered thousands of scientists, companies to be more productive in their day-to-day science work. I think Pangeo demonstrated that this sort of grassroots, bottom-up, user-driven approach is really more effective at delivering useful tools than a very top-down approach. And by top-down, I mean, an agency, let's just pick on NASA, says, okay, we need like a new science environment for our scientists. Let's design it and let's build this environment and then build it for them and then they all have to use it, right? And I mean, NASA didn't actually do that. They're actually very progressive, but you see that approach from different agencies. If we build it, they will come, right? And instead, Pangeo is very much co-developed in a much more interactive way with these tight feedback loops with the end users. And I think that's a key property. And finally, Pangeo has really pioneered what it looks like to do in big, large-scale environmental data science in the cloud. We were very early in the cloud, and we found some really cool patterns and technologies that unlocked a lot of new capabilities. However, I see a lot of limitations to the way we're doing Pangeo. So I don't think we're done with data infrastructure. And if I thought that, I wouldn't have had to go, start a company. It's really hard to operate this Pangeo technology. So it's great for expert users, but it's not accessible to the vast majority of scientists to use these tools. It's still too hard. It's still too technical. You still have to know too much about cloud and clusters and chunking and all of these things that scientists don't really care about. So there's more work to do. To deploy and operate this type of infrastructure as an organization is also very inaccessible. So we, with Leap, with quite a bit of resources and a lot of local expertise, we still struggle to find the right personnel, the right expertise to run our Pangeo system for us. So currently, Julius Buseke is our sort of Pangeo hero, bearing a huge amount of weight to keep that all running and support the users. Most organizations don't even have one Julius, and they just can't adopt these tools, and they need to stick with the status quo that they know and know how to use. I'm not sure that this approach to making all these different hubs is really getting us what we want. Sometimes I worry that we're just kind of recreating these silos up in the cloud rather than, or these fortresses up in the cloud rather than, in our basement, right? We have our Leap hub. That's great for Leap researchers, but what if we want to collaborate with someone who's not part of Leap? Well, what do? We don't have a great answer for that. And then finally, getting data into the cloud remains a big challenge. It's great once it's up there in an analysis-ready, cloud-optimized format, but how's it supposed to get there? That's not where it's originally coming from. It's coming from a FTP server in a NOAA data center somewhere, right? So who's supposed to do that, and how do we manage that data? Those are some of the big challenges. So that concludes like the middle part of this talk. And finally, I'm going to move on to where I see things headed and what are some of the trends, and sort of conclude with telling you about what we're doing in Earthmover. Right, so we started 10 years ago when big data was the big craze, right? Now, of course, AI is where everything is trending. And I see, mostly related to AI, I see three big trends that are happening that we need to sort of think about and respond to when we're planning the next wave of data infrastructure. One is just the presence of the private sector in environmental climate science. This was not really the case 10 years ago, but now we see across many different sectors a huge interest in climate data, whether and I'll include weather data especially as well in that. So whether that is from the financial sector that wants to have accurate climate risk information in order to make planning decisions, or insurance, or whether those are startups that are building AI-driven weather forecasting models, there is a new climate tech sector, and they want the same data that we as researchers want. And so how do we deal with that? The next trend is something I call everything, everywhere, all at once. A lot of our data infrastructure was designed for this idea that I want to query this point. I want data from this place in space and time, and let me search for it, and I'll pull out my little file. If you're training a big AI model, you basically just want all the data. You're going to just churn through all the data over and over to learn some model from it. And that's just a really different pattern. And so how do we support that use case? And then on a related note, it's really easy to at least produce a data set that is worth sharing with the world. Anyone can be a data provider. AI is enabling us to derive new data products in new ways, and we should get those out into the world. Most of our data infrastructure today assumes that there's a few big data providers like NASA and NOAA, and all the rest of us are data consumers, and that's sort of a one-way street. And I don't think that's accurate anymore. Okay, so I'll dive in a little bit on each of these trends. So private sector is here. I mentioned this already. Here is a sort of graph showing in just venture capital investment in the climate tech sector. And you can see it's really steep curve here. So a lot of different business models, a lot of different ideas that are being tried. But the bottom line is that there's a bunch of companies out there who want CMIP data and reanalysis data and remote sensing data, all the same data sets that we are using as inputs for our research. And it's very interesting to observe how they are approaching data infrastructure, which is very different from the way we do it in academia. On the other hand, they're hiring all our PhD students and postdocs to work at those companies, which I think is a great thing. And they're finding this sort of clash of cultures around how data is handled. As for everything everywhere all at once, last fall we had a really great talk about the ClimaX foundation model. There's a bunch of other foundation models that are out there now in climate and geospatial and weather space. And these foundation models are sort of inspired by the large language models, ChatGPT, et cetera, models that are just capable of consuming a huge range of unstructured data and in an unsupervised way, learning sort of a foundational latent representation of the entire problem space underlying that data. And they're super exciting. They're extremely data hungry, right? So these models can just chew through all of these massive data sets. And when I've spoken to the folks who developed this, what they said is, well, basically the main bottleneck where we stopped was we just weren't able to really get enough data and load data fast enough in order to keep training our model. And so that's how we decided where to stop training and made the model as big as we could. And so I think there's little doubt that removing that bottleneck will enable more and more powerful and capable foundation models to emerge. And then finally, this idea that everyone is a data provider. What I mean by that is it's easier than ever to create valuable planetary scale data sets. So just as an example, here are 3 new AI-based weather forecasting startups. They are using AI. They're using the same source data that most other people have, but they think they can do it better than ECMWF, right? It's bold. It's exciting. I wish them luck. But if they succeed, they have to get that data out to the world just the same way National Weather Service does. And so, what are they supposed to do? How are they supposed to provide that data infrastructure? So these are 3 trends. And what we generally observe is a phenomenon I call architecture soup, right? So I was at a conference in Vienna called Big Data from Space last year, and I went around the poster hall and I took pictures of everyone's architecture diagram of the cloud data system they were building, and they all looked crazy and they all looked different. And my main takeaway is there's just a huge amount of energy being expended in folks trying to figure out how to build and design these next generation of data systems. And from my point of view, we already have some pretty good patterns to start from. The basic architecture that we developed in Pangeo is very scalable, very effective, and meets a wide range of use cases. And so what I think we need are more building blocks, higher level building blocks that are just ready to go, so that an organization that wants some state-of-the-art cloud data infrastructure doesn't have to start by hiring a bunch of cloud engineers and sketching up some very complicated architecture diagrams and spending 2 years building some system, which, when I say it that way, it's clear that that is an option for almost no academic organizations, and it's very expensive for companies and startups to do. And instead, we need to be able to provide these sort of building blocks and components as a service that you can just swipe your credit card and get access to, right? And so here's an example of 3 companies that have all sort of spun out of this Pangeo world. The first one we're already partnering with here at LEAP. It's 2I2C, the International Interactive Computing Collaboration, and they provide Jupyter Hub as a service. So if you use 2I2C's product, you don't have to manage your own Jupyter Hub and figure out how to set it up and all that stuff. That's just provided as a service, and it's made it so much easier for us to provide that to our researchers. Another example is the company Coiled. They provide Dask as a service. Haven't talked much about Dask, but it's a scalable parallel computing framework that's great for working with data in the cloud. And finally, this brings us to our company, Earthmover. What we're doing is providing essentially a Zarr-based data lake as a service. So a home for an organization's data in the cloud, trying to incorporate all the lessons we've learned about how to manage data in the cloud over the past half decade working on Pangeo. So now I'm going to put on that hat as a startup founder and basically tell you what we're doing and what our product is. Right? So first of all, Earth Mover is a public benefit corporation. Right? So that means we are a normal for-profit company, but we have a mission statement written into our corporate charter. And that is to empower people to use scientific data to solve humanity's greatest challenges. What we've done is brought together folks like myself, experienced scientists, open source software developers who understand the problems that users actually face, with folks who have worked at companies like Google, AWS, Planet, who really understand how to build this sort of production grade cloud data systems. And so together we're building this platform. We're 8-person company today. So the way I describe this, the pitch I use to explain our product and our platform is the same one I started with. That the status quo is that Earth system data workflows are very painful, right? What they usually involve starts with a painful ingestion process whereby you have to extract a bunch of files from a data provider in all these different file formats. This is a huge drag. Then there's this whole data cleaning step, right? You have to organize those files, harmonize them, set them up so they're actually ready for analysis. Then finally, you get to do your analysis or modeling. This is the fun part. This is what we all look forward to as scientists. And this is not fundamentally different in industry. That same pattern exists. You have to ingest data, you have to organize data, and then you get to train some machine learning model or something from it. And then at the end of this, right, you can share your reproducible code pipeline if you haven't already gone crazy or gotten too frustrated, right? So the overall goal for our platform is to allow our users to stop thinking about files and instead start thinking about querying Earth system data like a database. Okay? So it's useful to take a little interlude to understand how sort of mainstream business handles this problem, right? Like leaving out like the Earth data part of it, like across the economy, there's a huge amount of data out there. Like all companies, have petabytes of data now that they want to operationalize and access. And this is a huge, sector of the economy. So what do they do? Like what does Walmart do when they want to get insights from their petabytes of customer data and store data and logistics data and everything they have? Well, almost every company in the world follows this pattern, which is that they're using the cloud, and they have something called a data lake or a data warehouse, which is a sort of central repository, source of truth for that company's data. And they have a data ingestion process that ingests data into that data warehouse, and then they build all kinds of what's called business intelligence applications on top of it. And there are different people who are responsible for different parts of this. And there are many different products out there that address the different parts of this workflow. And so, at the center of this is this data lake or data warehouse concept. And there exists this whole category of product that do this for people, right? And so Snowflake is a big example of that. Google BigQuery, Databricks, company you might have heard of that provides a data lake platform. And overall, this whole sort of set of tools is called the modern data stack. And for the most part, no one in our domain uses any of this stuff. But this is like a $1 billion economy here of products and services. So why don't we just use that stuff, right? Like that would ostensibly solve our problem, right? And the reason is that the data we work with in Earth system science doesn't use the same data model that typical business data use. So typical business data is what we call tabular or relational, basically rows and columns in a spreadsheet. Now maybe you've got 1 billion rows, but that's still the data model, right? Instead, we've got this gridded data, right? Climate model grids, weather model grids, satellite data, images, right? And so the data has a very different structure, and that means those off-the-shelf data systems that exist in the cloud don't really work for us. So what are you supposed to do? Right? So here are the different options that people have today. One is to use one of these existing data lake or data warehouse platforms as is. And that's still a valid option to consider because they're really convenient. Like it's really easy to set one of these things up. You don't have to do a lot of work to manage it. They have a lot of great features that help you govern and catalog your data. But of course, they don't understand this data model. So you have to somehow squeeze your data into this database in some really inefficient or suboptimal way. The second option, this is basically what we do in Pangeo. So we're going to use cloud object storage, this very low-level layer of cloud services to build our data lake on top of. And you can kind of do whatever you want there. You can keep this data model that we know and love from our netcdf files or whatever. But there's a lot more custom software development and architecture building involved in going down that path. So this is where we get into that sort of architecture soup diagram. You have to answer all these questions. Well, how are we going to catalog our data? And how are we going to ingest our data? And how are we going to control access to our data? And all of this complicated stuff that is also pretty generic. So what we're trying to do with our platform, which we call Xarray Lake, is to offer sort of the best of both worlds. To keep this data model that we know and love and want to use in environmental sciences, but provide that sort of convenience, that out-of-the-box experience that comes with one of these data warehouse platforms. So this is what we call Xarray Lake. So I'll just give you a quick tour of what it's like to use Xarray Lake, and then I'll wrap up. So you interact with Xarray Lake using standard Python code that you would be familiar with from Pangeo. So who here is a user of Xarray? Just curious. Okay, we got quite a few. That's great. So in our platform, you connect to what we call data repositories. So that would be this get repo. And then you open up a data set, and you can just write that to your repo using standard Python tools that we're all familiar with. What happens when you do that is you're ingesting data within this organized structure within Xarray Lake. And the data model we use in the platform is based on this Zarr data model. So we organize data into first repositories or repos, then folders or groups, and then finally coming down to the individual arrays, multi-dimensional arrays, and then split into chunks, right? Have support for all the common file formats. Now, what happens once you sort of add this data and commit it is that it automatically populates a data catalog. Do I have a zoom in on this? So here's an example of the data catalog in Xarray Lake. The minute you write the data, it becomes accessible and visible in a data catalog that you can go search against, browse against, sort of single source of truth for where what data lives in that data lake. Then you can pull your data out. You can find data through all sorts of different methods. In particular, we support search against all of the metadata in that data lake. So if you want to find everything that matches a particular CF standard name, if you want to find things that match a certain CMIP experimental facet, you search, find the data you want. You can do that in the web. You can do that from the command line. A huge part of what we built is essentially aimed around making Zarr and this cloud data format work a little bit more like a database. And that means implementing what we call ACID transactions, the ability to atomically update the data and roll back those changes if the update is not successful. This is a really sort of technical, nerdy feature, but that is really important for building stable system that can be used in a production context. And that means, if you're a bank or an insurance company who wants to use, Zarr type data in your processes, these capabilities are really crucial to doing that safely and reliably, and are quite different from the way it works today, just dumping data into object storage. And so with this comes a full audit log of how the data is evolved over time, and who updated it when, providing huge amount of transparency into the history of your data. So the way this platform works, I'm not going to get into this in too much detail. I'm realizing the slide is a little bit too technical, but we're basically building a metadata database that keeps track of all of this metadata in all of these different arrays, groups, files, across potentially petabyte scale data lake. This is just the beginning of the platform we're building. So I'm just going to walk through what our sort of near-term roadmap is. So right now, what we're working on is building what we call API gateways, sticking APIs on top of this data that allow folks to query it in all kinds of more flexible ways. So it can be as simple as OpenDAP, various APIs like Open Geospatial Consortium that allow you to quickly pull out points, view your data as a map, things like that. We're really excited about this next thing that I'm just going to tease. It's called seamless arrays. If you've ever been frustrated with how to chunk up your data, this is for you. That's all I'll say. And then finally, going forward, we're going to explore hosting public data within Array Lake. A lot of the data sets that folks want to use, whether it's ERA 5, whether it's CMIP6, are already are used across many different users, many different potential organizations. And so if we can provide those part of the platform, that could potentially be very, very valuable. Here's an example of one of our customers, a company called Silvera. They do carbon credit monitoring, reporting, and verification focused on forest carbon. And so they are using Array Lake as their sort of internal central database for all their remote sensing data. They were able to migrate off Earth Engine and speed things up a lot by adopting our platform. So, who are we aiming this at? Companies large and small, as a system of record for business critical environmental data. Public sector, we think is a great fit for public sector agencies that are trying to migrate their data system to the cloud. And finally, we think this can be really useful for academia to help a research project or a department or an entire university modernize their approach to storing data. So to summarize and sort of wrap up, I'm really excited about the cloud. I think it has enormous potential to help us move into the future of Earth system science, but we need to make it way easier to use. And so that's a big part of the motivation of what we're doing at Earth Mover. And there's many other folks who are pursuing the same goal. If we can achieve that, sort of the real vision is that we can move into sort of planetary scale data federation in the cloud, where different organizations can really seamlessly and with very low friction share data with very high bandwidth, right? So what I mean by that is if a startup like I mentioned, Xcarta wants to train their model on petabytes of NASA's remote sensing data, they can just do that. They don't have to ingest, they don't have to do some expensive downloading process. And of course, we, Leap, have a big role to play in this as well, as both consumers of data and as providers of data, as the sort of AI-enabled climate models that we are working towards start to come online. We want to find a way to share that with the world as well. So if we can make the cloud easier to use, make it more accessible to adopt these type of technologies, I think we're going to unlock huge amounts of new science and new applications for Earth system data. So that's it. A little bit of time left. Thanks a lot for listening to my story.
Great. Thanks so much, Ryan. Lots of food for thought. Any questions, maybe starting with early career scientists?
Yeah, this is a question for my team at AI2, so it's not just me. We're doing a lot of ML training, and Zarr v3 has small chunks. How's that going? I mean, I know you're excited about AI. This seems like a great fit for AI applications, but getting into the nitty-gritty training loop, how do you get those small chunks without zillions of files?
Let's take that question offline. I think it's a long technical answer. There's a lot of work happening there. I don't know if I can provide you a satisfactory answer in this context.
Hi. So you mentioned that industry and academia deals with data quite differently, I believe. I'm just wondering if you could speak more about that and why that is the case.
Yeah, I mean, for the most part, the biggest divide, I would say, is just if you're starting a an AI startup, like there's no question you're using the cloud. Like no one even really considers not doing that. For the most part, in academia, we are not using cloud. Like Leap is the exception. Like most universities, it's just like servers in the basement. And so that is at the large scale, like the biggest divide. And when I've seen it happen over and over, you know, a PhD student will come out of an academic lab and then go to one of these startups, and all of this new technology will then be thrown at them. And so, you know, they'll have to very quickly try and learn all of this, you know, cloud computing stuff. And it's a very steep learning curve. And so that's what I was referring to.
It's because academia is just, I guess, older, more long-standing, right? Whereas this industry places, they're newer. So over time, academia will also shift over to cloud. Do you think that's a trend?
I believe very strongly that there are very good reasons to be using cloud, not purely just technical or financial ones, but in terms of enabling better collaboration. But I don't know that the IT departments in universities that are making these decisions see those incentives or have any reason to move away from the status quo. So I'm not very optimistic about that in the short term. I see the universities as being pretty conservative and mostly incentivized to maintain what they already have. The people who are running those systems would lose their jobs if they move to the cloud. So there's really, you know, I mean, of course they could retrain, but I mean, the point is, I don't know that the incentives are there for universities to make this migration. What we mostly see is individual projects trying to use the cloud, like Leap, which is good, but it's not really receiving support from the university at, like, say, the university IT department level.
Thank you.
And in the back, then yeah.
We do have one question online from
yeah, sure.
Shanice. Shanice, do you want to unmute yourself?
Hi, Shanice.
Hello.
Shanice.
So I might have missed this when you were talking about data lake or array lake, but when you commit your changes in array lake, I'm assuming it saves like the modified data. So is storage a concern when you have, you know, different people doing different processing on the same raw data and you're committing it?
Yeah, that's a great question. So I didn't really get too much into the technical details here, but the way this system works is a lot like Git. If you've ever used Git and you made a commit in your Git repository, we're just saving a diff or a delta. So you can think of the state of the data that you're creating as like building up from these diffs or deltas. So it's a very efficient way of storing the data. It does not cause like a large explosion of the amount of data. You don't like copy the data every time you create a new version, for example. Okay, yeah, there's some folks back there.
Yeah, I have a question about the pre-processing of the data.
Yeah.
I have a question about the pre-processing of the data, like CMF6. There are multiple organizations, multiple model versions, and they always have different processing that we need to do in real science. I just wonder, like, if you also aim at like included that part into your big projects.
We want to allow our users to do that work really efficiently. Just about everyone has to do data cleaning, right? And so what that looks like in Array Lake is you can perhaps have the raw data that you've ingested directly from the data provider, and then you can have a processed, clean version of that. As your data moves through its pipeline, it can move from raw to processed to finally, usually, you know, AI-ready form where you've really organized it in a way that's suitable for model training. And so you can store all those different layers of the data within Array Lake. We can't automate that pre-processing for you. It looks different for every data set, but we can make that work a lot easier.
We can contribute back to the data set in the Array Lake.
So if you are an Array Lake customer, you own your own data. Like, it's not our data. You sign up for this, and if your company, you know, or, you know, like decides we're going to use Array Lake, you're not giving the data to us. It's your data. We're giving a tool to help you manage the data. You store whatever you want. Yeah, in the back.
Thanks for the talk. So I actually, something that came to my mind and maybe bothers me the most when working with data is that, for instance, when you go to Netflix, it just keeps showing you what you want to watch and tries to tempt you with what you want to watch. But when you come to scientific data, you have to really go out of length to look for and find what you want. Like you cannot just specify keywords. This is what I'm interested. So what do you have? And give you suggestion. There's no database. There's no resource.
Yeah.
So I wonder if something like this can be doable within your platform, and if so, what would be required, either by you or by the people that are customer?
Absolutely. So it's a huge part of our goal is to enable users to find the data they want more easily. And that starts by just having a one central point that is our data catalog. You can go, you can browse the data, and you can search the data. So that exists today within Array Lake, and I think it's much easier than having to comb through 100 different data providers to find the data you want. So I think already we have something for you. We don't have recommendations of what data you liked Era 5, land. Wait till you see Sentinel or like we could go there for sure. That requires a lot of user data, and we just have few users right now because we're very new. But it's a really great suggestion.
Maybe we'll take a last question. Then there's going to be food in the back, yeah. So please come over.
You kind of started at the beginning by like posing these two components of science, of simulation and then data intensive science.
Yeah.
And you made a very strong case for moving the data component to the cloud. Do you see the simulation component moving to the cloud? Is that desirable?
Really great question. And it really gets at the challenge. It's the weak part of my argument. For operational running of, say, weather models or climate models, it is currently not nearly as cost effective to do that in the cloud as it is to do that in a custom-built data center just for that purpose. And that's because those workloads are very predictable. So if you know exactly what you're going to be doing with your simulations, as most climate modeling centers do or weather prediction centers do, you just buy the exact hardware you need, scope it to that problem. That's much cheaper. Cloud is great when you don't know what you're going to do. You're exploring, you want to scale up, you want to scale down. It's much more cost effective and flexible. That's a problem. What we really need to solve that is, and this kind of gets to this federation idea, like it doesn't just have to be like cloud or not cloud. We can build connections between cloud and between other data centers. It's really, the cloud is really just the internet, right? And so if we have enough connectivity between, say, NOAA data centers and NASA data centers and cloud computing, data can flow seamlessly between all of those. It's not quite what we have today, but it's certainly feasible to build that, and that's what I'd like to see.
Okay, great. So thanks again, Ryan. Yeah, and again, there's going to be food in the back and a lot more happening today for Leap Day again. Thanks everyone for joining.